Okay, so the topic of today's lecture is something called closed form matting. Okay, and even though there have been other matting algorithms that have been proposed since then, the core idea of this closed form matting that we're going to get to kind of by the middle or two-thirds way of the lecture is still really important and used in a lot of matting algorithms. And so this approach and the other one that I'm going to talk about at the end of class, these were both devised by a really cool researcher, Levin, who has done some really cool computer vision research. And so her stuff is really always very interesting and always very kind of clean to read how she comes up with these ideas. So let's remember what we're trying to do, right? So what we're trying to do is we have an image that is alpha times a foreground image plus 1 minus alpha times a background image. And so last time we talked about Bayesian matting, which was kind of an initial attempt, kind of a probability idea for taking the foreground and the background distributions that we estimate from the image. Those came from this trimap that we had this kind of certainly background, certainly foreground, and then don't know region, and use those to estimate kind of simultaneously the alpha, foreground, and background at every pixel that kind of maximize the probability of observing the given image. So one thing that was not so great about Bayesian matting was that there was no enforcement of kind of temporal coherence in the mat. Even though things often worked out pretty well, you really had nothing that constrained, the alpha at one pixel to be very similar to the alpha at another pixel. And so today we're going to talk about an algorithm that really does try to take those kinds of constraints into account. And so one thing that, if you go back to, and of course, I don't think I actually have it loaded up here, but I can do it. Oops, okay, sorry. So if we go back to a picture from last time, this guy. So what I want to get at is that we had this picture of distributions of foreground and background pixel intensities. And so here was a picture that kind of was, again, my toy with the blue screen. We had this very small blue background cluster, and then we have this foreground cluster. And the observation here is that the foreground cluster, in this case, looks kind of like a long, skinny ellipse. And so it turns out that there have been some perceptual studies and some studies of real natural images that show that if you look at a very small window around a pixel, that those colors are all lying on a straight line in color space. And so kind of a better illustration of that is given by this thing. So the idea is that, not across the entire image, but if I just were to take a small window around a pixel, say a 5 by 5 window, and I looked at the colors in that window, you would see that they generally lie close to a line. And so this is what this researcher Levin called the color line assumption. And so the idea is that within a small window, all the colors lie, in this case, these are the foreground colors. Basically, how do we describe a line in 3D space? Well, we say there's kind of 2 points that lie on the line, in this case F1 and F2, and then every color in the foreground window, Fi, is roughly somewhere along that 3D line that connects those two things. And similarly for the background. So the two background colors that define the line could be very different. But again, this is the hypothesis. Okay, so this is kind of like the starting point. And so actually, when you do the homework and you start to look at your images, so I'm asking you to take a real image where you have a real foreground and a real background. I don't think it takes too long to convince yourself if you just kind of take little regions of pure background and little regions of pure foreground. I think you can see that this color line assumption really does hold pretty well. And so the color line assumption kind of mathematically says that the foreground and the background colors in a small window lie on a straight line in RGB space. And it's important to realize that this really only holds within some small region. Okay, and so what I kind of want to say here is that the line depends on which window we choose. And that kind of makes sense, right? So, for example, if you think about, me as the foreground and this wall as the background, well, if I were to take just like some sub-chunk on this wall, it's easy to believe that since this is almost a constant region, that, that would be a straight line. Something like this whiteboard, where maybe there's a gradation of kind of white to gray depending on the lighting from your perspective, again, that gradation would be a straight line. But, it wouldn't be the same straight line as if I took a square that was in the middle of this monitor here that was all black, right? So basically, as I move this window around, I get different straight lines, okay? And of course, I can't make the window too large, otherwise that assumption may be violated, okay? And so this is kind of the idea that we're going to work with for the whole lecture. Yeah?
Does it make sense to think about this or look at it in like another color space?
So that's a good point, and so RGB is not always the best color space to look in. And it's true that if I linearly transform RGB, or if I transform RGB to some other color space, I may not get the same linear relationship. I don't know whether it's been looked at when you transform the color space. That's a good question. And actually, it wouldn't be too hard to verify whether it is or it's not, right? Yeah?
It seems like this assumption would also be violated if you hit an edge.
Right. So that's a question of, okay, so what happens if I'm like over this edge, right? So again, if the edge is roughly between, kind of two constant color regions, then you can kind of argue that I'm still okay, right? So if I have a black edge, so suppose I have something like this, right? So then, in RGB space, maybe one of the endpoints is close to 0, 0, 0, and one of the endpoints is close to 1, 1, 1, and most of the points are either here or there, but you could still argue that those points are close to that line, right? Now, if you have something like this, where, there's a white, part of the screen, there's a black band, and then there's this thing here, well, then you could say, okay, well, maybe that violates the assumption. So the question is, how large should I take my windows so that I'm always kind of more in this situation than I am in something where I'm spanning like multiple edges. Okay. And actually, I didn't really prepare for it. I'm not sure whether I can do this on the fly, but let's test my powers here. So, what image is this? Okay, so this is a toy that we're going to come back to later in the class. And so, I'm thinking about what the best way to do this is. If I was smart, I would have planned this out before lecture, but we'll see what we can do. So let's just grab a location on this image. Okay. And so let me take a little image that is this image centered around, say the 25 pixels that are nearby here. I guess it should be 290. So basically, now if I look at this little image, I would have to really blow it up to actually see anything. But so here's a little image patch, right? Which is maybe even too small for me to make bigger in MATLAB for some reason. But let's agree it's tiny. So now what I want to do is I want to, all right, this is going to be kind of quick and dirty. So MATLAB, as you know, is like, a vectorized language. So you should always avoid doing for loops, which is exactly what I'm doing right now. But let's just say I am going to plot the little m of I comma j comma, this is really crude. I apologize because I'm usually known as being a pretty slick MATLAB guy, but this is not slick MATLAB. And let's not get too fancy here, but okay. I didn't do the for loop on the top guy. So let's see here. Looks kind of scattery, but again, you know, if I were to make this axis scale a little bit better, so let's say I should probably make these on the full 0 to 255 scale.
I think it's just accents.
Oh yes, like this, right? No, I like this. What? Vector must have, oh, I see. Oh, MATLAB. Let's see if this works. Okay. So now when you kind of look at it in this perspective, right, we can see that these colors are all kind of like, you know, kind of clustered together. And if I were to rotate this around, you know, this blob, you know, is probably not a bad fit to a line, you know. I mean, it's one of these things where the closer you get to a blob, the less it looks like a line, right? But in this case, I think that we could make a pretty good case that, you know, if I were to look at this as an ellipsoid, a small ellipsoid, and draw the line along the major axis, it wouldn't be a horrible fit. In some sense, I'm kind of surprised it's not better, but I hadn't really worked on this example. So let's come back to this, and I may fool around with it a little bit and post another comment on Piazza. And I'll also see that, you know, I'll see if I can find the original paper where people kind of studied exhaustively a whole bunch of natural images to talk about why this assumption is justified. So it didn't just come out of nowhere. I mean, this came out of some existing studies. Okay, so what is the meaning of this linearity assumption, right? So basically, mathematically, that's like saying that every foreground pixel I is like some mix of some basic color foreground 1 and some other basic color foreground 2, right? That's kind of like saying, you know, foreground 1 is this color, foreground 2 is this color, and beta kind of tells me how far along the way am I from foreground 1 to foreground 2. And this beta changes for every pixel in the window, right? So the idea is that for a given window, F1 and F2 are fixed, and then for a given pixel within that window, I have to say, well, what fraction of the way am I between foreground 1 and foreground 2? Okay. And in the same way, background I is some combination of some canonical background pixel and some canonical other background pixel. And this is kind of corresponding to the figure I showed you earlier. Okay. So how does this help us at all? Okay. So one really interesting observation was that if the color line assumption holds, then the true mat alpha satisfies alpha I equals so what does this mean? Well, this is kind of surprising. This says that if I just look at this window by itself, that I can obtain the correct alpha value just by a simple affine transformation of the intensity. So it's like saying, if I knew the color, I multiply that 3 vector of the color by some other 3 vector A. So this here is going to be 3 by 1. This here is also going to be 3 by 1. And this B is just a scalar. So it's like saying that the true alpha values are just a simple transformation of every color. And that's kind of a surprising result. That's kind of like saying that if we knew this A and B inside the window, that I could just easily transform the original image right into the alpha map, right? That would be a pretty exciting result. And so let's show why this is true. Okay, so I mean, it's kind of interesting to think about, where this even comes from. So let me just say, why is this true? And this is actually a good little linear algebra exercise. So let's go back to our original equation. Right, this is basically saying that at pixel I have some unknown alpha, some unknown foreground intensity. Right, this is just the standard matting equation. And now I'm going to plug in what I know about the foreground and the background. These things are, by the color line assumption, kind of linear combinations of these points on the line. So I could say this is like the Fi is actually the equation that I have from before. And then the background is similarly some combination of known background points, right? This is by the color line assumption. And so now what I'm going to do is I'm going to rearrange this in a clever way, okay? So let's think about this. What I want to do is I want to, let me just expand this a little bit to be super clear. This is also an exercise in just expanding things. Okay, so what I want to do is I'm going to move this B2 over to the left. So what I'm going to have is, on the left-hand side, I'm going to have I sub I minus B2. And on the right-hand side, what I want to do is make this into a like a 3x3 system. And the things I'm going to choose here is you can see that in some places I have alpha I by itself. I'm going to put that over here. And then in some places I have an alpha I beta I. And in some places I have a gamma I minus alpha I gamma I. So again, this is kind of like one of these magic things where you have to see the trick. So let me just show you that I can write things in this form. So what multiplies alpha I? Well, let's see. I have an F2 and I have a minus B2. So basically I can say I have F2 minus B2 is the first thing that multiplies this. I'm really abusing the linear algebra here because actually this it would be more accurate to say this is a row vector. So let me just say this. In MATLAB world, maybe what I should say is that I have this thing. What multiplies alpha I beta I? Well, I have an F1 and I have an F2, so I have F1 minus F2. And what multiplies this gamma E part? I have a beta 1, a B1, and I have a B2. And that accounts for all these terms I've got. So let me rewrite this in a slightly not so messy way. So I'm going to rewrite exactly this on the next page. So what did I learn? I learned that all these things are related in the following way. So this here is a 3x1 vector. And what I have is I have this 3x1 vector, this 3x1 vector, and this 3x1 vector. And that's getting multiplied by this 3x1 vector. remember, I put all these slides, scan them in, and put them on Piazza. So you don't have to necessarily write down everything that you're seeing here. And this is also in the book, right? So maybe better just to kind of follow along instead of trying to concentrate on writing all the notes. So again, each of these guys is 3 by 1. And this guy here is also a full 3 by 1 guy here. Okay, so how does this help us? Well, now what I want to do is I want to basically get the alpha over here by itself. So I'm going to take the inverse of this matrix, right? So this is like a big 3 by 3 matrix by itself. So I should be able to say that alpha I, plus the other stuff, is, this big matrix inverse times this vector from the left-hand side, right? So this is a 3 by 3. This is 3 by 1. And so what does that mean? That's like saying that if I just look at the top, row of this matrix, right? So what I have now is, how do I do matrix vector multiplication? I have something like this. And that's like saying that the way I get alpha I is by multiplying this, vector, let's call it R1 transpose, times this. So that's like saying that alpha I is R1 transpose II minus B2, which is the same as saying I have something times this minus something times this. So this here is, this R1 is a 3 by 1 vector, and this guy here is a 1 by 1 number. And so this is the proof of the claim I made earlier that's saying that inside this window, the alpha is related to the color by this linear transformation, where I have this and I have this. And I didn't give you the actual details of what's inside all these matrices, but the big picture is that all this stuff here, really all the stuff that's in this matrix and all the stuff over here, it only depends on, the original endpoints of these color lines, right? And so this is just kind of like the proof of the claim that, in fact, if we buy the color line assumption, then we have this relationship with the alphas. Okay? And so the idea that comes from this is that you could say, okay, well, how could I use this observation to help me with the matting problem? Okay. So how does this help with matting? Well, it kind of suggests a cost function that I could try to minimize, okay? Because, we're all real-world, hands-dirty kind of people. We actually want to set up a cost function that says how good a mat is, and we want to minimize that cost function, okay? So here's a candidate cost function for how that might work. That's like saying, okay, let's call my cost function J. What do I need to figure out? Well, for every pixel, I need to figure out its alpha value. And for every window in the image, I need to figure out these A and B that satisfy this linearity assumption. And so the way I would say it would be what I would say is I would sum over all the pixels in the image. So sum over all pixels. And then for each pixel, I would sum over basically all the pixels that are inside the little window around that pixel. And what do I want to minimize? I could minimize the difference between the alpha at that pixel and the color line assumption. So it's basically saying, over all the possible pairs of pixels and windows, I want to figure out, how good my assumption is that the alphas match up with this color line assumption. Okay. So, again, at first blush, this doesn't seem like a very useful thing to do, right? Because I still have a lot more variables than I have equations, right? So it's like saying that at every pixel I know exactly one thing. I know the color. That's a three-dimensional vector. And here, I'm asking myself to estimate at every pixel the alpha value and this three-dimensional vector A and this one-dimensional number B. That's 5 numbers, right? So I'm still trying to estimate 5 things when I only have 3 pieces of information per pixel. So we're going to talk about how we can resolve that in just a second. But let me just back up by saying what I started at the beginning of the lecture, is that, why is this any better than kind of a Bayesian matting approach? Well, one reason is that there are kind of tight constraints between the things that have to happen at different pixels. So, for example, that's like saying that, at this pixel in the image could be part of, a bunch of different windows, right? It could be at the one corner like this, or it could be like this, or it could be like this. And in the same way, like this pixel over here, it shares a window with this pixel in a couple places, and other places it doesn't, right? So the point is that collecting the pixels together into these windows enforces coupling between the pixels. So no longer is the estimate at this pixel like totally an independent thing from this pixel, because they're being kind of grouped together because they're close by in a window. So this pixel and a pixel over here are going to be still not very involved with each other because they're not directly related, but pixels that are within kind of a window's length of each other are going to be nicely related. Okay. So this thing provides us a way of getting a little bit of nice spatial coherence to making sure that we don't have alpha values that vary like crazy over the whole image. Okay. Okay. Questions or comments? So let me preface this whole chapter by saying that it's unfortunate that, in a way, I know I kind of come up with a bang. You're seeing all these equations like, right away, right? So this chapter is actually fairly mathematical compared to the other chapters. And so you shouldn't necessarily think that you're going to get 14 weeks of lectures like this, right? We're going to talk a lot more generally and a lot more visually about a lot of other topics in the class. So don't be scared off by the first few lectures, okay? Flip forward in the book, convince yourself that there's more nice stuff coming, right? And actually, if I'm being honest, if I had to do it again, I might consider swapping chapters 2 and 3, because chapter 3 is much more light and fun and interesting than chapter 2 is. But by the time I had this thought, it was way too late to re-vector everything in the books. So unfortunately, it's the way it is right now. Okay, so getting back to this. So now how are we going to help us out? So this again, I think is, I find it interesting just because I think that one thing, just as an aside, that's really good for engineers, both undergraduates and graduates, to understand is how do you go from a problem like this into some sort of like a linear algebra problem that I can solve, right? So I think a good skill is like, anyone can kind of think about, okay, here's a good, idea for minimizing something, but being able to rearrange that into something that kind of makes some sense in terms of being able to do it very easily in MATLAB, for example, that's a skill that's important to develop. And so this is kind of a case study of how that might work. So let's start with this. Okay, so what I want to do is I want to rearrange this equation, which has this kind of double sum notation, into something that is much more matrix-y. Okay? So here's what I'm going to do. First of all, I'm going to try and remove this inner sum. Okay? So the J sum here is basically indexing the windows, right? So it's like saying, make a pixel around each window. So I'm going to keep that guy for the moment. And I'm going to say, okay, what I have is this sum. And then what was the original equation saying? This is basically saying I want to do this sum of squares over all the pixels in the window, right? And so let's think about what are the things that I really need to figure out here, right? So really, the only things that depend on this index j are the linear values I need. I need to know this A and I need to know this B. So those are my unknowns. That's like saying that within each window I have 4 unknowns. So it's always good to be able to write my, I'm going to write this kind of thing like this. So we're going to have a big norm. That's like saying the length of a vector. What don't I know? Well, I don't know AJ and BJ inside the window. So this is a 4x1 vector that I don't know. And what does this tell me that I want to do? This tells me I want to look at the difference between this scalar and this scalar, and that's going to be the entry of a vector, right? So how do I get the difference? Well, what's multiplying AJ for the first pixel? Well, I'm taking the color at the first pixel in the window, and that's what this AJ transpose I is. And then I have a 1 over here, right? So that's my AJ transpose I1 plus this B constant. And I'm comparing that to the alpha 1 here. And so in some sense, you know, this gets a little bit messy in terms of notation. This is like kind of like saying here, this is like saying the first pixel inside the jth window. And this is the first alpha inside the jth window. And then I would just populate this matrix in the same way, all the way down to how many pixels do I have in the window? Well, let's call that number W, okay? And then this comes down like this. So, just as an additional wrinkle, I'm also going to add a little term here to this cost function, right? So what I'm going to add here is just a little term that says, you know, all things being equal, I want to add this. What does that adding do? This is like saying, okay, I'm going to penalize this A vector from becoming too large. Okay. In a way, what that does is it prevents the maths from getting too far from a constant. So what does that mean? So if, let's think about the equation here. So let's suppose that A was 0. That would mean that the mat inside that window would just be a constant value, right? And in some sense, we want to kind of bias mats to being, you know, roughly constant as opposed to mats being crazy. So this is what you'd call a regularization parameter to kind of make sure that that doesn't happen too much. And so that means that when I add this thing here, that I also have a little bit of a extra row here that basically takes into account the fact that I have a regularization term. So this here is basically the last column is just for the regularization. Don't worry too much about that. So big picture, right? Let's just not worry about the forms of these matrices. What this is like saying is that for every window, I have some big matrix, let's call it capital GJ, times this vector that I don't know, minus this vector of alphas, let's call that alpha j. Okay? So I have, you know, these guys here depend on image colors. And then these guys here are unknown and need to be figured out. And so what I want to do, right, the whole point of this is I want to make sure that this vector is close to that vector for all the windows, right? So how do I minimize, this difference? And so each of these guys, so minimizing each of these is a linear least squares problem. Right? So what we really care about is alpha. So it's like saying, suppose I told you what this vector was, how would I find A and B to bring those two things as close together as possible? Well, so suppose we knew alpha. What A and B make this number as small as possible. Well, that's just like a linear least squares problem. So those of you who have done like the pseudo inverse know that the best thing that I can do, and I'm going to put a little asterisk to indicate this is like the optimal thing I can do, is to basically do the pseudo inverse, right? So this is basically saying this is the pseudo inverse of this matrix. So that's like saying that I can't necessarily maybe satisfy this equation exactly, but the best I can do is this least squares solution. And so this is a clever way of saying that, okay, well, that means that if I told you alpha, I would know exactly the right A and B to use. So in some sense, this says that A and B are exactly functions of alpha, right? And so this is nice. It says that A star and B star are functions of alpha. That means that we can take this whole problem, right, and turn it into a function of alpha. So the whole problem is a function of alpha. What I mean is that I can take my original problem that I'm trying to solve and say, hey, if I knew this, I would know that. And so I'm going to plug in, what do I know here? So I basically have a new function that only depends on alpha that says that I sum over all the pixels in the image this thing. I have Gj times what I know would be the optimal solution. Okay. And so this is a pretty exciting result. This basically says that, what I can do is this is now only a function of the n alpha values across the whole image. So I've gotten rid of all this kind of too much information or not enough information issue. And actually, this can be written in a nice way. So this is like, again, what I could do is I could write this like I take a vector of all the alphas in the image. So this is all alphas in the image. And I can rewrite this cost function as this nice vector times some huge matrix times this vector, right? So this is like a 1 by n vector. This is an n by n matrix. This is an n by 1 vector, right? And so this L, right? This L basically can be built from, you know, the image colors. Right, so all the stuff that I need to build this huge matrix in the middle is just the colors of the original image. Okay, and the form of this is fairly messy. It's a combination of a bunch of things that look like this, right? So actually writing out what every element in L is just a real mess. But the exciting thing is that we've made this a super clean equation, right? So again, if I was going to write this in a vectorized form, so if I make kind of this bold alpha where, you know, if I had a different color pen, but this is basically saying this is the vector of all the alphas, my problem now looks like this. And that's a really easy problem to solve, right? So if I want to minimize this thing, how do I do that? Well, just like with any minimization problem, I take the derivative with respect to alpha, and I set it equal to 0. What do I get when I take the derivative of this and set it equal to 0? So the derivative with respect to alpha, here alpha is a vector, but we can still do it, is 2 times L alpha equals 0. So the result is that the alpha that I should choose satisfies this simple linear system. This is an n by n matrix, this is an n by 1 vector, and this is a vector of zeros. And again, hopefully from linear algebra you remember that this is what you call an eigenvector, right? This is actually the eigenvector of L that corresponds to the 0 eigenvalue. So this is also called a null vector of L. So we took this really complicated optimization problem that we didn't really have any insight about how we were going to solve it, and we turned it into something that MATLAB can do very quickly, which is just looking at the eigenvalues of some big matrix that I can construct. Okay? And so that's a pretty nice result. So this L here, this L is a really important quantity that they call the matting Laplacian. And so if you look at the literature, you see this phrase, matting Laplacian, used a lot. And it's just made up of image colors arranged in a certain way, right? It's not hard to build this Laplacian from image colors in a kind of a natural, procedural way. Luckily, you don't have to do that yourself. There's code out there that you can use to build it yourself. Okay, so let's step back and think about this for a second. So what this means is that any eigenvector of this big matrix that has a 0 eigenvalue will satisfy the matting equation. Okay. So the bad news is that there are many 0 eigenvectors. That is, that if you look at this L matrix, it turns out to have lots of eigenvalues that are either exactly 0 or really close to 0. And so that means there's still some uncertainty about which alpha should I choose. Okay. But this is where so far, all this mathematics was done without any user intervention at all, right? I just would build up this L matrix just from the image intensities, and then I would solve this equation and set it equals 0, right? I haven't used the user input at all, and that's where the user input is really important. So the user input comes from, like, for example, these scribbles on the image. So to constrain the mat and get what we want, we need user input, which could take the form of, for example, scribbles. Basically what that says is that there are some pixels are forced to have alpha equals 0, right? That means that we know that those are background. or alpha equals 1, we know that they're forced to be foreground, right? And so really the problem that we want to solve is something like this. So we actually solve something like, I want to minimize this quantity plus something like lambda times the sum of 1 minus alpha I, where I is in foreground scribbles. So I would do something like this in practice. I wrote it a little bit differently in the book, but it's kind of along these lines where we say, okay, so this thing I want to minimize for sure, but I want to put a big penalty. So this lambda is like some huge number. And that's like saying, I am seriously forcing at every foreground pixel that the user scribbled on that alpha has to be 1, right? Making lambda really a huge number kind of forces that to be true. And in the same way, where I've scribbled on the background, this is definitely background, I'm forcing alpha to be equal to 0, right? This term here enforces that the mat is consistent with the user scribbles, okay? And so I'll show you just a second, just to take a break from the math, to show you the piece of code that actually does this. But this is really what's actually happening kind of under the hood, okay? And the really exciting thing from a mathematical perspective was that this researcher at Levin showed that if the color line model held and if the matting equation was accurate, so if you produce the image exactly from the matting equation, and if the scribbles were all consistent with the true underlying mat, so the user didn't screw up any scribbling, then basically when you solve this problem, you get exactly, so the ground truth mat, the true mat, will always minimize this equation. And that means that you can always get to the true mat if you just kind of keep on scribbling enough, right? So there may be some iterative process where you have to, initially scribble a little bit, see what you get, scribble a little bit more, see what you get. And that's really the way the process works in practice. And so here is and this is actually one of the homework problems, is for you to basically go out, take a picture that makes the matting problem a little bit difficult. Okay, so something where you've got some sort of a frizzy hair, find a friend with goofy hair, or find a stuffed animal or something like that. Take a picture, and then I want you to try and apply this kind of canned algorithm to that picture and see what you get. And what you're going to find out probably is that maybe your first mat is going to kind of suck, and you have to go in and re-scribble on the image to say, okay, no, this over here is background, this over here is foreground. There's this kind of iterative process of seeing what you get. And so there's a link in the homework file to the zip file full of code that you can use to do this. And let's see here. So I believe, what did I do this on? So I think that I did it on my Willow picture. Oops, where do we go here? I guess I have to close my other figures here, because I did hold on. Okay. Right, so here's the image that we talked about last time. So how did I handle the matting of this image? Well, what I did was I went into Photoshop or something similar, and I scribbled on it. Let's see here. I forgot what I called it. Willow scrib, oddly enough. So I basically scribbled on it, where I said, okay, everything that's under a white pixel has to be foreground with alpha equals 1. Everything under a black pixel has to be background with alpha equals 0. Okay, and this, in some sense, I think that I probably went a couple iterations on scribbling like this. So when you do this, I think that what you have to do is you have to have a Photoshop or Paint program window open in one thing, and then what I do to run the algorithm is I just basically say run matting on my original image and my scribble image. See if this works. So it takes a couple minutes, or a couple seconds to run. So one observation while this is running is that, don't try to run this code with basically, your 2000 by 3000, image that comes right off your digital camera. What I would say is take a nice picture. And it's important, again, one thing that is good for these kinds of problems to really illustrate the concept is to have a camera that has a little bit of depth of field, meaning that if you look at my original Willow image, well, I guess it's hard to see here, but the original Willow image, the foreground is in sharp focus, and the background has this nice kind of, pleasant green fuzziness to it, right? That means that I've focused my camera nicely in on the foreground, and the background is kind of left to fade out. That's, appealing from a photographic point of view, and that's also good from a matting point of view, too. So I would say, if you have a friend who has a decent camera, as opposed to just using your first cell phone picture that you take, try to take a decent-looking picture of something fuzzy, okay? And you'll notice that in the alpha matting website, most of those matting problems also are in places where, they've got some nice background and they've got some sharp foreground, okay? Now, once you've got this beautiful picture, then you want to downsample it or you want to resize it so it's not so huge, right? So I would say, this image is probably not more than maybe a few hundred pixels wide, like maybe 300 pixels wide. That's going to be a small image by modern standards, but the thing to remember is that when you build this matting Laplacian, right, so if I go back to this, so this L that has to be created as part of this process is n by n, where n is the number of pixels in the image, right? So if you've got even a 300 by 400 image, right, that's already, what is it, 120,000 by 120,000 matrix that you have to get into your computer memory, and then you have to do the eigenvalues of that, right? So if you took like a image that was 1,000 by 1,000, then you've got a Laplacian that's 1,000,000 by 1,000,000, right? And you're going to rapidly run into problems on your computer. There are better computational ways of doing this, but the code that is provided on this webpage is not going to help you with that, right? So don't go all whole hog on some massive image immediately. So let's see what this eventually gave us. So let's see. The first figure is just showing me that it's figured out what the strokes are. So the way that the program works is it looks at the scribble image that you give it, and it finds all the pure black and pure white pixels. So this is like all the strokes that the user gave, and then I think these are just the foreground strokes, right? Just check those images out when you run your program to make sure that you've got the right strokes. And then figure 3 is the resulting alpha mat, which, looks pretty good. In fact, I think this is probably the same alpha mat that I was showing you last time. It's got like nice fuzziness around the edges, and this final figure, I think, shows the foreground multiplied by the alpha mat. That's the kind of thing that I could take this thing, I could put it back on some other background, and this is like the background with the alpha mat times the foreground removed, and you can see that not much of this pussy willow blossom remains in the background, right? This means that we've done a nice job of totally sucking off the foreground from the background, right? And I think this is exactly the map that I used to show putting this onto the other background, right? So, so it can work pretty well, okay? But like I said, I think that I probably went through a couple of iterations of drawing scribbles on the foreground and the background to say, okay, no, you need to make sure that you constrain the mat in this region, right? So one of the homework problems is to just basically do this on one of your own images and fool around with it and see how it works, just to give you some sense of this scribbling process. Okay, so let me pause to take a breath and ask, are there any questions? So again, I know especially in the derivation of this manual Laplacian that there's lots of lots of math to follow along with. And it's not critical that on the first time that you see it, this all makes sense magically, but you should kind of look into the equations in the book and see, okay, I kind of see how I got from step A to step B. Question?
Yeah, I forgot not the form of the adding Laplacian, but just from the equation that kind of looked like, so if the matting Laplacian has like a trivial null space, and it means that there is no foreground, is that makes sense?
Well, kind of what it means is that the matting Laplacian by itself has a large null space, okay? And it always will because of the way it's constructed. And the scribbles are needed to force yourself out of this null space, is what it comes down to. And it may be that by adding the scribbles that you actually aren't getting a vector that is right in the null space. Instead, you're getting a vector that is as close as possible to the null space as you can get, right? So that's kind of the idea. Is, I mean, again, under ideal circumstances, the ground truth mat will still be in the null space with L alpha equals 0. In practice, because of the way you take the picture, you may not satisfy exactly all of these equations, but this number will still be really small, right? And I think that, again, if you kind of dig into the code a little bit, you'll see the place where the Laplacian is created. And if you want, you could just look at the eigenvalues of that and see how many of them are really small, right? Actually, that kind of folds into what I'm going to talk about next, so let me come back to that in a second. Other questions or comments? Okay. So here's an idea that, again, it was kind of like follow-on from this original work. Okay, so basically, this was a paper in one of the big computer vision conferences, or maybe it was in SIGGRAPH one year, and the next year they came out with another kind of refinement to this approach. And so the refinement was based on the following observation. So what we want to do is we want to basically find, basically we seek alphas that are eigenvectors of L with eigenvalue 0. These are also called null vectors, right? L alpha equals 0. Okay. Now, it turns out that there are a lot of these, right? So there are, it turns out, many such eigenvectors. Okay? So it's not like there's only one eigenvector that satisfies this. As it turns out that there are lots and lots. Part of that comes from the structure of the Madding Laplacian. It turns out the Madding Laplacian is very sparse, and that sparsity lends itself to having a bunch of very small eigenvalues or 0 eigenvalues. And so the question that these people asked was, is there something that we can do with these eigenvectors? And so let's go to my pictures here. So I guess this is just the picture I just showed you. So, here is a toy, right? So if I were to form the Madding Laplacian and look at the eigenvectors, right? The eigenvectors can be kind of interpreted as, so again, let me just go back here. So basically this L is n by n, where n equals the number of pixels in the image, right? So an eigenvector of L, so say I have LV equals 0, V is some n by 1, or I guess it's actually like an n, actually no, it's like actually, get this for a second. So, yes, that's right. So V is n by 1, and what I could do is I could turn this long, skinny vector back into what looks like an image, right? Because in some sense, what I did to create L in the first place was I took all the pixels in the image and I laid them out like a long column vector. Once I've got an eigenvalue or an eigenvector, I can take that long thing, I can turn it back to something that looks like a grayscale image. And so if I do that for this example, what I get are, here are the first, few eigenvectors interpreted as images. So I get this thing, I get this thing, I get this thing. And so, these are not, on the one hand, I couldn't use any of these guys directly as maps, right? So these all satisfy L times this eigenvector equals 0, but this, for example, would be a very poor mat for the image, right? It doesn't really match what I think of as a correct map. But it does have some promising properties, right? It does kind of follow around the contours of the object, right? I mean, I can really pick out the toy from this. Whereas a lot of times, eigenvectors, this could be, for all we knew, some sort of like crazy random noise-looking image, but it doesn't. It looks actually like it follows along with the contours of the image. Here, this almost looks like a grayscale version of the original image in some sense. And here, again, this looks kind of like a negative version of the image. And so the insight was, well, hey, what if what I tried to do was I tried to combine these eigenvectors to make a vector that is as binary as possible, right? So if I could do that, such a combination of eigenvectors would kind of look like what I want a mat to look like, right? So if I can just restate that here. So interpreted as grayscale images, each eigenvector probably looks like a poorer map, right? So even though I may have something that satisfies this, that V, when I look at it, could be kind of a crappy looking map, okay? But, so there are many zero eigenvectors. So what if we try to combine multiple null vectors to make kind of what I would call as binary as possible maps? Right? That's like saying I have a whole bunch of V's such that each of these guys equals 0. That means that if I were to take some new W and I said, okay, I'm going to take, beta 1 times V1 plus beta 2 times V2 plus beta K times VK, right? If I look at LW, that is still going to be an eigenvector, right? Because these guys are going to pop out. I'm going to get, basically B1 LV1 plus ... and each of these guys is 0, right? So any combination of 0 eigenvectors is still going to be a 0 eigenvector. But what I can try to do is I can try to arrange these guys in such a way that I get something that is better or perceptually closer to a mat, right? And how could I force it to look like a mat? What I would want to do is, I know that almost everywhere the mat is going to be almost 0 or almost 1, right? Remember that picture I showed you last time where I looked at the, the plot of alpha for a real image and it looked, kind of something like this? That's like saying that almost all the time alpha is pretty close to this or pretty close to that, right? And so that's kind of what I want to do is I want to take all the null vectors that I can find, right? Take all the small eigenvectors that I can find and try and combine them in ways that look like they are partially, mostly binary, right? And so the idea is, for example, say we have 100 kind of grayscale-ish eigenvectors. The idea is to transform them into 100 binary-ish, real precise eigenvectors, which may be better for matting. Right? Because I have total freedom, right, to say, okay, again, this is kind of a linear algebra way of thinking about things. If I have 100 vectors, all of which are linearly independent, what I could do is I could just kind of like rearrange those vectors into a new basis that everything is still linearly independent, but those vectors have more desirable properties, right? And so, without going into the details of how this optimization works, it can be done, okay? So basically, what you do is you basically make a cost function that kind of is the opposite of this picture. It's kind of like saying, okay, instead, what I want to do is I want to have an alpha cost function that looks like this, where the cost is low if alpha is close to 0 or 1, and it's high if alpha is close to somewhere in the middle, right? So it's kind of like taking this picture and inverting it to say, okay, I want fractional alphas to have high cost. And then what I can do is I can try to minimize the alphas, I can kind of like minimize the sum of the alphas in these transform mats to have as low cost as possible. And so I can do this, and this is an idea that they called spectral matting. And it's called spectral matting because the eigenvalues are also known as the spectrum of a matrix. Okay? And so what is the virtue of this? What is the point of doing this? Well, the point of doing this is, again, that this is just like saying, okay, I get the matting Laplacian only from looking at the image colors, right? I get the eigenvectors of that matrix without having any user interaction at all. And this process also of transforming the eigenvectors doesn't involve the user either. So far, the user has not scribbled on the image or even looked at the image, right? And so the nice thing is that when you look at the results of this, so if I do this kind of reshuffling the eigenvectors to be as binary as possible, these are the results of doing that algorithm. And so here, you can see that this is like the first binary-ish image. And you can see that, hey, actually, this isn't a great mat either, but it has some promising properties, right? It's black in the background, and it's, got pieces of the foreground. It almost looks like, it got a little bit of this animal, a little bit of this animal here. This is the second eigenvector. So now, again, it's black everywhere in the background, and I got some of the animal's nose and some of its front. Here, I've got, kind of, if you look at this is kind of like saying, well, here, again, the mat is pretty good in the front of the animal, pretty poor in the back of the animal, but actually, maybe I could make that up with another image. The fourth eigenvector doesn't look like it helps us. Fifth one doesn't look like it helps us. Sixth one gets the part of the animal in the butt that we didn't have before, right? And so here's the idea is, okay, let's call these things matting components, right? So the idea is that you do this pre-processing on the image, and you present the user with this menu of matting pieces. And you ask the user to select the ones that they think contribute to the mat that they want. And so if I look at the, here's the seventh one. So if I look at the sum of the first, 4 good-looking mats, I get this, right? And this is actually already well on the road to being a good mat, right? So the idea is that this is maybe an interface for the user that is easier to use, right? All this computation is done offline. At the end of that process, the user gets a menu of these somewhat binary matting components, and they just kind of click on or off the ones that they want to contribute to the map. And then this is like their initial map to start with. And maybe still there's something that needs to be done, right? So if you look at this, you can see that, things are not purely white in this region, and things are not purely black in this region. So probably the user then needs to step in and maybe do a little bit more scribbling. But the point is that there's already a lot of work that's already been done to get a pretty good looking map, right? So this was a kind of an interesting approach, right? The idea being that you defer the user interaction until you're sure that you've got something that is, already pretty good for them to work with, right? So you can read more about the way that this interactivity works after you add up these components. And I think that this is just a picture kind of showing, again, these are the first 6 eigenvectors, and I kind of outlined it in black. I should have outlined them in red. That if I add these guys up, I get the mat on the right, and that looks pretty good. Okay, so I think that I've probably hit you with enough math and information for the morning. So let me just give you a kind of sense of where we're going next, okay? So there's also this really important overall computer vision concept called Markov random fields, and we're going to talk about those next time for matting information. And that kind of way of thinking about a problem actually is going to be useful to us for other things that are going to come up later in our discussion of visual effects algorithms. And then, so that's going to be on, what is it today? Today is Thursday, right? So we're going to talk about the Markov random field stuff on Monday, and then on Friday we're going to talk about basically come back to the relationship between hard segmentation and matting. And so there are some very often used in computer vision algorithms for quick kind of scribble-based segmentation, and those are actually kind of neat algorithms to learn about in their own right. And we'll talk about how you could do something where you obtain a hard mat, like binary, literally 0 or 1, and kind of upgrade that to something that has softer edges by kind of fuzzing out the edges. And so kind of that's where we're coming up next. So remember that, again, the homework is on Piazza, so you should be able to make a crack at maybe about half of it at this point in time, right? So basically, there are a couple paper and pencil problems that involve just kind of fooling around with equations. There's one, you can start thinking about going out and taking your image and starting to fool around with this code. So what I'm asking you to do on the homework is to take your image, run this closed formatting code on it, the one with the matting Laplacian. Also, there's spectral matting code that you should be able to get to work on this on your image. For the spectral matting code, you may need to compile and download a couple of smaller packages, but the README file does give a little bit of information about how to do that, and I or the TA can hopefully help you work through that a little bit. Again, what you'll see in the spectral matting code is you'll be presented with like this menu of matting components, and you just try and pick the ones that work. And again, if it doesn't work for your image, that's not the end of the world. I just want you to see how it works and to try it and to go from there. And then I'm also going to ask you on your image that you take to do this hard segmentation based, just like what would you get if you kind of used a scissors to cut out the foreground using, again, a piece of code that you can download. We're going to talk about that stuff next week, but you can kind of get started on that, before then if you want. Please don't try to do the homework like the day, before it's due, because, well, I don't think it's brutal. It's not the kind of thing that I want to figure out all at once. So try and work on some of these problems continuously as the concepts start to click in and make sense. My office hours are this afternoon. Usually they start at 3, but since there's a faculty candidate, they're going to start at 4. So if you have any questions, feel free to come by between 4 and 6. Okay, great. So I'll see you next week.
The spectral matting, is that alternative to scribbling?
The spectral matting is prior to scribbling, right? So then you can imagine that if you scribbled on the image, you could refine the map that you got from the spectral pieces. Now,
well, in your example here, you look like you scribbled beforehand.
For this example, for the closed formatting, I scribbled beforehand. For the spectral matting, there's no scribbling until you kind of do the first clicks, right? And then there's some refinement process afterwards.
So my SIS said